Say it again.
Hydrogen sulfide ion?
The hydrogen sulfide ion, which is HS minus.
Oh, yeah, I read it wrong. I mean...
No, I think you said it right. Hydrogen sulfide. It's the, oh, you said hydrogen sulfite.
Yeah.
Also an amphoteric substance. Hydrogen sulfide is HSO3 minus. Can you find it in two places? HSO3 minus. One acting as an acid, the other acting as a base. Yeah? Here's a question we don't ask. Which is it stronger as, an acid or a base? It's like saying, do you walk to work or take your lunch? You're talking about two different things. The HSO3 ion acting as an acid is different than the HSO3 ion acting as a base. They're different things. So we don't compare the strength of something as an acid to the strength of that same something, that amphoteric substance, as a base. We don't do that.
Could you compare two amphoteric substances to each other?
You could compare two things that are acting as acids, and you can compare two things that are acting as bases. But you're not going to take one thing acting as an acid and compare it to another thing acting as a base and say who's stronger. How are we doing? Okay? Now, back to the equation and the double arrows. Which did we decide was the stronger base? Water or nitrite ion? Acting as a base, where would you find the strongest base? At the bottom, the HNO2 minus ion, huh? Right? The conjugate base of NH3. That's the strongest base. The weakest base would be the top right, the perchlorate ion, ClO4 minus. Yeah? So, acting as a base, what's stronger, water or nitrite ion? The nitrite ion is stronger, isn't it? It's closer to the bottom, acting as a base, right? Again, don't be confused by the fact that water appears twice in the table. You can say, well, wait a minute, the water's up near the top. Acting as a base, it's up near the top. Near the bottom, it's acting as an acid, right? So, if this is the stronger base, then wouldn't you expect this reaction to be more able to go this way than that way? Because here's what we have. We have two bases. Key point here. We have two bases that are competing for the hydrogen ion. It's a little tug of war. Here the hydrogen ion is attached to the nitrate ion and the water molecule is trying to take it away. Over here, the hydrogen is attached to the water molecule and the nitrate ion is trying to take it away. Yeah? Who should win the tug of war more of the time? The nitrite ion. Now, that's not to say because it's stronger it wins all the time. Did we talk football last time? Yeah. Take the worst football team and the best football team and put them together. Is the best team guaranteed to win? We know that's not true. Okay? The Raiders managed to win some games last year. You know, even though they sucked pretty bad. So, in the tug of war, who's going to win this tug of war most of the time? The nitrate ion, which means this reaction is more likely to go backwards than forwards. Now, what's that mean? The more of these we get, the more of these we have, and the more of them we have, the more often they're going to win the game. In other words, if we have the Raiders playing the Giants, that's what we talked about, right? If we had the Raiders playing the Giants, but we had fewer games, no, that parallel is not going to work. No, that's not going to work either. Here's one that is used classically.
Sammy.
This is
done
the
with it, ask
profile
for break.
of the back of a car going down a bumpy road. Okay, so there's a low level in the back and then a higher level. And there's a bunch of balls rolling around. Okay, and you're going down a bumpy road, so the balls are just knocking around. And every once in a while, a ball ends up here. Right? How does it end up there? Well, the balls are bumping around and bumping into one another and bouncing around, right? Random motion. Yeah? Because of the bumpy road, the balls are moving randomly. Some are moving fast, some are moving slow. Depends on their collisions, right? So, if the balls are bouncing around, every once in a while, one of them is going to get hit hard enough to go up here. But of course, these balls are bouncing around, right? So once in a while, every once in a while, one of these ends up down here. Now, where would you expect to find most of the balls at any one particular time? Down here, huh? But that doesn't say that there's no balls up here, right? Just because this is where the balls have the lowest potential energy, that's what we're talking about. That's what nature likes, huh? It doesn't mean that all the balls are going to end up down there, necessarily.
Just really quickly point out what
The car is like, you know, I'm up here in the driver's seat. It's the back of the car.
Like the back seat?
truck.
It's a truck.
Truck, but the bed has 2 levels.
Yeah.
We got it now?
You gotta drive it, not truck. Makes more sense that
Sometimes it'll. That's okay, but it's
Oh.
How's that? Is that better?
Yeah.
It's out of time. You have Eric.
Alright, now what does this have to do with this? Well, where do the hydrogen ions want to be?
The lower part of the truck.
Attached to the nitride ion, right? The nitride ion is the stronger base. So the hydrogen ions want to be attached to the nitride ion. Where do the balls want to be? Down here, right? That doesn't mean that some of them aren't going to be up here. Here's the key. Here's the key. This is chemical equilibrium. Another example, one that we are going to talk about extensively between now and the end of school, of what we call chemical equilibrium. This dynamic state of equilibrium. 2 processes, one undoes the other, right? And we end up with kind of a balance of some sort. But the balance doesn't mean we have equal amounts on each side of the arrow. Which way does the reaction want to go? In this case, it would prefer to go in the backwards direction rather than the forwards direction, right? Doesn't mean it's all going to go backwards and we'll end up with all of this and none of that, right? Because we also have the forward direction that is producing the products. Is it time? Yeah, let's take a break.
Wait, so it's that little arrow.